Tonight, we're going to explore something that sounds like science fiction, but is actually one of the most brutal realities in all of physics. Deep space. The region beyond our planet's protective bubble. You've seen movies about astronauts floating through space, heroes venturing between stars, colonies on distant worlds. But here's what those movies don't show you. Deep space exposure involves something most people completely misunderstand. And by the end of tonight, you're going to see why the universe beyond our planet isn't just dangerous. It's hostile in ways that attack every system your body depends on. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something you already understand: survival. You know what it takes to survive in your everyday environment. You need air to breathe, water to drink, food to eat, a relatively stable temperature, protection from the elements. These are basic requirements that your body has evolved to expect. Earth provides all of these things automatically. The atmosphere contains oxygen at the right concentration, roughly 21%. The temperature stays within a range that allows liquid water to exist. Gravity holds everything in place. The magnetic field deflects harmful radiation. The ozone layer blocks deadly ultraviolet light. All of this happens without you doing anything. It's the baseline, the default state of existence that your biology assumes will continue. Now, imagine removing each of these protections one by one. That's what deep space does. It strips away every single thing your body needs to survive, all at once, instantly. Deep space isn't just empty. It's actively hostile in ways that are hard to overstate. Let's start with the most immediate problem: pressure, or more accurately, the complete lack of it. Right now, sitting wherever you are, you're experiencing atmospheric pressure. About 14.7 pounds per square inch, or 101,000 pascals. That's the weight of the entire column of air above you, pressing down. It doesn't feel like anything, because it's pressing equally from all directions. Your body has evolved to operate under this pressure. Think about what that means for a moment. Every square inch of your body is experiencing nearly 15 pounds of pressure. Your entire body surface area, roughly 20 square feet for an average adult, is under about 43,000 pounds of total force. That's over 20 tons of pressure. You don't feel it crushing you because there's equal pressure inside your body pushing back out. Your blood, your tissues, the air in your lungs, all of it is at the same pressure as the atmosphere around you. It's balanced. Equilibrium. This equilibrium is so fundamental to how your body works that most biological processes depend on it. Your cardiovascular system pumps blood through vessels at pressures carefully regulated relative to atmospheric pressure. Your respiratory system depends on pressure gradients to move air in and out of your lungs. Even your cells maintain osmotic pressure balances that assume external atmospheric pressure. The human body is a machine calibrated to work at 1 atmosphere of pressure. Take that away, and the machine breaks down catastrophically. Your lungs work because of pressure differences. When you inhale, your diaphragm expands your chest cavity, creating lower pressure inside your lungs than outside. Air rushes in to equalize the pressure. When you exhale, you compress your chest, creating higher pressure inside than out, and air rushes out. This entire process depends on having atmospheric pressure as a baseline. Your blood, your bodily fluids, the gases dissolved in your tissues. All of these exist in equilibrium with atmospheric pressure. Now picture what happens when that pressure disappears. Instantly. Completely. This is what's called exposure to vacuum. And the effects begin in less than 1 second. The first thing that happens is ebulism. That's the formation of gas bubbles in bodily fluids. Here's how it works. At normal atmospheric pressure, gases like oxygen, nitrogen, and carbon dioxide remain dissolved in your blood and other fluids. The pressure keeps them in solution, the same way a closed bottle of soda keeps carbon dioxide dissolved in the liquid. Think about what happens when you open a soda bottle. That hissing sound is carbon dioxide coming out of solution, the bubbles that form and rise to the surface. That happens because you've reduced the pressure by removing the cap. Inside your body, you have gases dissolved in all your fluids. Nitrogen makes up about 78% of the air you breathe, and it dissolves in your blood and tissues. Oxygen dissolves too, though most of it is carried by hemoglobin in red blood cells. Carbon dioxide, the waste product of metabolism, is dissolved in your blood as it's transported to your lungs. All of these gases are in equilibrium with atmospheric pressure. When you suddenly remove that pressure, just like opening a bottle of soda, those gases come out of solution. They form bubbles everywhere. But unlike a bottle of soda where bubbles just rise harmlessly to the top, in your body, these bubbles form inside your circulatory system, inside your tissues, inside your organs. And they cause immediate, severe damage. But when you suddenly remove that pressure, just like opening a bottle of soda, those gases come out of solution. They form bubbles everywhere, in your blood, in your saliva, in the fluid around your eyes, in your tissues. The medical term for this is decompression sickness, though you might know it as the bends. Scuba divers can experience a mild version if they surface too quickly from deep water. But what happens in the vacuum of space is incomparably more severe. It's not a gradual pressure change from a few atmospheres to one. It's an instantaneous drop from 1 atmosphere to essentially 0. The bubbles form everywhere at once. Your blood begins to foam. Your tissues swell as gas expands within them. The water in your mouth, your throat, your lungs begins to boil. Not from heat, but from the lack of pressure. This is vapor pressure boiling. Water normally boils at 212 degrees Fahrenheit or 100 degrees Celsius at sea level pressure. But the boiling point of water depends on pressure. At lower pressures, water boils at lower temperatures. At the top of Mount Everest, where pressure is about 1/3 of sea level, water boils at about 154 degrees Fahrenheit or 68 degrees Celsius. In the near vacuum of space, water boils at body temperature, 98.6 degrees Fahrenheit or 37 degrees Celsius. Your saliva boils on your tongue. The moisture on your eyes boils away. The fluid in your lungs begins to bubble and froth. This sounds like something from a horror movie, but it's pure physics. It's what happens to any liquid in a vacuum, and the physics behind it is well understood. The boiling point of a substance depends on the vapor pressure needed for molecules to escape the liquid state. At higher external pressures, molecules need more energy, more kinetic motion, higher temperature to overcome that pressure and escape. At lower external pressures, less energy is needed. In a perfect vacuum, essentially no external pressure, molecules can escape the liquid state at any temperature above absolute 0. Your body temperature is 98.6 degrees Fahrenheit, or 37 degrees Celsius. That's far above absolute 0. more than enough for water molecules to escape into vapor in a vacuum. So the moisture in your mouth, your throat, your lungs, the surface of your eyes, all of it starts boiling, not violently like water on a stove, more like a rapid evaporation, flash boiling into vapor that immediately disperses into space. This has been observed in experiments. Not with living subjects, obviously, but water exposed to vacuum chambers behaves exactly this way, instant boiling at room temperature. The same physics applies to the fluids in your body. Now, here's something most people don't realize about space. When we talk about the vacuum of space, we're talking about different levels of vacuum depending on where you are. Space isn't completely empty. Even in interstellar space, far from any star or planet, there are about a few atoms per cubic centimeter. That might sound like nothing, and compared to Earth's atmosphere, which has about 10 to the 19th molecules per cubic centimeter, it is effectively nothing. But it's not absolute zero pressure. It's just so close to zero that the difference doesn't matter for our purposes. Near Earth, in low orbit where the International Space Station flies, there's slightly more matter. The outer reaches of Earth's atmosphere extend hundreds of miles up, getting thinner and thinner. At the ISS altitude, about 250 miles up, there are still enough air molecules to cause drag on the station. Not much, but enough that the station gradually loses altitude and needs periodic boosts to maintain its orbit. This is called orbital decay. Without those periodic boosts, the ISS would eventually spiral down and burn up in the atmosphere. But even at that altitude, the atmospheric pressure is about 1/1,000,000,000th of sea level pressure. For human purposes, it's vacuum. Exposure to it would have all the same effects we've been discussing. Further out, beyond Earth's atmosphere entirely, the density drops even more. In deep space, far from planets and stars, you might find 1 atom per cubic centimeter, maybe less. That's as close to perfect vacuum as you can get in nature. And that's the environment humans would face on a journey between planets or between stars. Pure, nearly perfect vacuum. No pressure, no protection. Nothing between you and the cosmic radiation streaming through space. At the same time, the gas in your lungs expands. Your lungs at normal pressure contain about 6 liters of air. In a vacuum, that air tries to expand to fill infinite space. If you're holding your breath when exposed to vacuum, your lungs rupture almost immediately. The expanding air tears the delicate tissue. This is why scuba diving instructors teach you never to hold your breath when ascending. Even the pressure change from 10 meters underwater to the surface, about 1 atmosphere of difference, can rupture lungs if you hold your breath. Going from 1 atmosphere to 0 is far worse. But here's the thing. Even if you don't hold your breath, even if you exhale as quickly as possible when exposed to vacuum, you still only buy yourself a few more seconds. Because the damage from embolism is already starting. And that's just the beginning. Let's talk about oxygen deprivation. Your brain consumes about 20% of your body's oxygen, despite being only 2% of your body weight. It's an energy-hungry organ, constantly processing information, maintaining consciousness, keeping your body's systems running. Without oxygen, brain cells start dying within seconds. In a normal environment, if you hold your breath, you have maybe a minute before you pass out. Maybe 2, if you're trained. But that's with your blood still carrying oxygen, with residual air in your lungs. In vacuum, you have no air in your lungs. It's been forced out by the expanding gases, or it's escaped through your mouth and nose. Your blood is starting to foam from embolism, which means it can't carry oxygen effectively, even if there was any to carry. Consciousness fades within about 10 to 15 seconds. That's how long it takes for the oxygen already in your bloodstream to be consumed by your brain. After that, you're unconscious. Brain damage begins within minutes. Complete brain death within 4 to 6 minutes. But you won't last that long. Because while your brain is shutting down from lack of oxygen, several other catastrophic processes are happening simultaneously. Remember those gas bubbles forming in your blood? They're causing circulatory problems. Massive ones. Your heart is trying to pump blood through your arteries and veins, but now that blood is full of bubbles, gas bubbles can create blockages, preventing blood from flowing properly. This causes areas of tissue to be starved of oxygen and nutrients even faster than they would be from simple lack of air. Your heart might even start pumping foam instead of liquid blood. At this point, even if you were somehow rescued and repressurized within seconds, the damage would be catastrophic. The bubble formation, the tissue damage, the oxygen deprivation, all of it compounds. People have survived very brief exposure to near-vacuum conditions in accidents. There are documented cases from the 1960s when spacesuit failures exposed astronauts to near vacuum for a few seconds. They survived because they were immediately repressurized. But they described feeling the saliva on their tongue boiling. They described feeling their skin swelling. They lost consciousness within seconds. And these were exposures of maybe 10 to 15 seconds at most. A longer exposure would be fatal. No question. But we're not done. Because pressure and oxygen are just the first problems. Let's talk about temperature. Space is cold. Everyone knows that. But what does cold mean in the context of space? Most people think of space as having a temperature of absolute zero, negative 459.67 degrees Fahrenheit, or negative 273.15 degrees Celsius. The coldest possible temperature where all molecular motion stops. That's not quite accurate. Space itself doesn't have a temperature in the conventional sense, because temperature is a measure of how fast molecules are moving. In a vacuum, there are so few molecules that the concept of temperature becomes complicated. What does exist is thermal radiation. Everything with a temperature above absolute zero emits electromagnetic radiation. The hotter something is, the more radiation it emits, and the shorter the wavelength. Very hot objects emit visible light. Cooler objects emit infrared radiation. Even very cold objects emit some radiation, though at very low intensities and very long wavelengths. The cosmic microwave background, the leftover radiation from the early universe, fills all of space and has a temperature of about negative 454.75 degrees Fahrenheit, or negative 270.42 degrees Celsius. Just a few degrees above absolute zero. So if you were floating in deep space, far from any stars, you'd be surrounded by this faint microwave radiation at negative 270.42 degrees Celsius. That sounds lethally cold. And it is, eventually. But here's the counterintuitive part. You wouldn't freeze instantly. You wouldn't turn into a block of ice in seconds like you see in movies. The reason is that heat transfer in space works differently than it does on Earth. On Earth, you lose heat through three mechanisms: conduction, direct contact with something cooler; convection, heat carried away by moving air or water; radiation, emission of infrared light. In a vacuum, conduction and convection don't work because there's nothing to conduct heat to and nothing to carry it away. The only way you lose heat is through radiation. And radiation is a relatively slow process for something at body temperature. Your body at 98.6 degrees Fahrenheit or 37 degrees Celsius emits infrared radiation. In the absence of any external heat source, you'd slowly cool down as you radiate heat away. But it would take hours, not seconds. The immediate threats in space, the pressure problems, the oxygen deprivation, would end you long before freezing became a concern. That said, if you were somehow able to survive the vacuum exposure, if you had unlimited oxygen and perfect pressure protection, but no thermal insulation, you would eventually freeze. It would be a slow, gradual cooling. Your extremities would cool first, then your core. Eventually, your body temperature would drop low enough that metabolic processes shut down. Hypothermia, loss of consciousness, death. But again, this would take hours, not seconds. The movie image of someone freezing solid instantly in space is pure fiction. There's also the opposite problem: heat. If you're close to a star, anywhere in the inner solar system, for example, you're being bombarded with intense radiation. The sun pours out energy in all directions. Near Earth, the solar radiation delivers about 1,361 watts per square meter. That's called the solar constant. Half of your body might be facing the sun, absorbing this energy. The other half faces away into cold space, radiating heat away. Without an atmosphere to distribute heat, one side of you would heat up while the other side cools down. You'd experience extreme temperature differences across your body. The sunward side could reach temperatures above the boiling point of water. The shadow side could drop to well below freezing. This temperature gradient would be uncomfortable if you were conscious, but again, you wouldn't be conscious. The vacuum exposure would have ended you long before the temperature extremes became the main problem. So pressure and temperature are catastrophic threats, but there's more. Let's talk about radiation. Earth's atmosphere and magnetic field protect us from a constant barrage of radiation coming from space. This radiation comes in several forms. Solar radiation, the stuff coming directly from the sun; galactic cosmic rays, high-energy particles from outside our solar system; solar particle events, occasional bursts of charged particles from solar flares. Most of this radiation is blocked or deflected before it reaches the surface. The atmosphere absorbs a lot of it. The magnetic field deflects charged particles, channeling them toward the poles, where they create auroras instead of hitting the ground. We're protected without even realizing it. To understand just how much protection Earth provides, consider the different types of radiation and how they're stopped. Solar radiation includes the full electromagnetic spectrum: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Most of this passes through space without any problem. It's just electromagnetic radiation, photons traveling at light speed. The visible light obviously reaches us. That's what allows us to see, to have photosynthesis, to have solar panels. Infrared radiation, heat, reaches us too. That's part of how the sun warms the planet. But the high-energy end of the spectrum, ultraviolet, X-rays, and gamma rays, these are mostly blocked. The ozone layer in the upper atmosphere absorbs most UV radiation. What gets through, UVA and some UVB, is what causes sunburn and tanning. But the really damaging UVC is completely blocked. In space, there's no ozone layer. All that UV radiation hits directly. UV radiation damages DNA by causing chemical changes in the molecular structure. It can cause mutations in cells. Over time, it leads to skin cancer. A person exposed to the full UV spectrum in space would get severe burns on exposed skin within minutes. Not from heat, from radiation damage at the cellular level. The skin would redden, blister, and eventually develop lesions. This is separate from the other problems we've discussed. This is purely from UV exposure. Then there's X-rays and gamma rays from the sun. The sun produces these during solar flares and coronal mass ejections. They're high-energy photons that can penetrate matter. On Earth, they're absorbed by the atmosphere before reaching the ground. In space, they pass right through. A solar flare, producing intense X-ray and gamma radiation, would irradiate anyone in space who wasn't shielded. The radiation would penetrate tissue, damaging cells throughout the body. But solar radiation, as dangerous as it is, isn't even the worst threat. The real danger comes from galactic cosmic rays. These are atomic nuclei, atoms stripped of their electrons, accelerated to enormous energies. They come from outside our solar system, produced by supernova explosions, neutron stars, black holes, and other violent cosmic events. When a star explodes in a supernova, it releases energy equivalent to the sun's entire lifetime output in just a few seconds. That energy accelerates particles to speeds approaching the speed of light. These particles, mostly protons but also heavier nuclei, like helium, carbon, oxygen, iron, shoot out into space in all directions. They travel through the galaxy for millions of years. Eventually, some of them pass through our solar system. And when they hit Earth, most are deflected by the magnetic field or absorbed by the atmosphere. We're protected. In space, there's no protection. A galactic cosmic ray is a single atomic nucleus moving at perhaps 90% of light speed. It has kinetic energy millions of times higher than particles in the most powerful accelerators on Earth. When it hits human tissue, it doesn't just damage the cell it hits. It creates a cascade of secondary particles. It ionizes atoms along its path, ripping electrons away, creating a trail of chemical damage. It can shatter DNA molecules. It can destroy cellular machinery. A single cosmic ray hit can kill a cell outright or mutate it in ways that lead to cancer later. The energies involved are just enormous compared to biological scales. Now, one cosmic ray hit won't end you. You're exposed to some cosmic rays, even on Earth. They make it through despite the atmosphere. You're constantly being hit by particles. Most pass through harmlessly. Some hit cells and cause damage. Your body repairs most of that damage. That's what DNA repair mechanisms do. But the dose makes the poison. On Earth, you're hit by maybe a few cosmic rays per square centimeter per second. Most don't cause lasting damage. Your risk of cosmic ray-induced cancer from a lifetime of Earth exposure is tiny. In space, the flux is much higher. hundreds or thousands of cosmic rays per square centimeter per second, depending on solar activity and location. That's because Earth's magnetic field and atmosphere normally block most of them. Over time, this higher flux adds up. Each hit has a small chance of causing cancer or other damage. More hits means higher probability. Astronauts on the ISS, who are partially protected by Earth's magnetic field, still receive radiation doses about 150 to 200 times higher than on the ground. A 6-month stint on the station increases lifetime cancer risk by about 1%. That might not sound like much, but it's 1% added to whatever baseline risk you already have. For a young astronaut with decades of life ahead, that's meaningful. And that's in low Earth orbit, with partial protection from the magnetic field. Beyond Earth's magnetic field, in deep space, the radiation environment is worse. NASA has estimated that a round trip to Mars, about 18 months to 2 years total mission time, would expose astronauts to radiation doses that increase cancer risk by about 5%. 5% added risk. That's considered on the edge of acceptable for trained volunteers who understand what they're signing up for. But it's far from safe. And Mars is relatively close. A mission to the outer solar system would take years. More time in deep space means more accumulated radiation dose, more cancer risk, more potential for other radiation effects like cataracts, cardiovascular damage, central nervous system effects. There's evidence that radiation exposure can affect cognitive function. Studies on animals exposed to cosmic ray analogs show changes in brain structure and behavior. Memory impairment, reduced problem-solving ability, increased anxiety. Whether these effects occur in humans from space, radiation exposure is still being studied. But it's a concern for long-duration missions. You can't have astronauts on a multi-year mission developing cognitive problems. The crew needs to stay sharp, able to make complex decisions, respond to emergencies, complete their mission. Radiation-induced cognitive decline could be catastrophic. Shielding helps, but not as much as you might think. You'd assume that thick walls would block radiation. And they do, to an extent. But cosmic rays are so energetic that they can penetrate meters of material. Practical spacecraft can't carry that much shielding. Every kilogram of mass has to be launched from Earth. More mass means more fuel needed, more cost. There's a limit to how much shielding is feasible. Current spacecraft have thin aluminum hulls, maybe a few millimeters thick. This provides almost no protection against cosmic rays. It blocks some solar particles, but cosmic rays punch right through. You could add thicker shielding, maybe water tanks surrounding the crew compartment. Water is actually better shielding than metal for cosmic rays because it doesn't produce as many secondary particles. When a cosmic ray hits aluminum, it can shatter aluminum nuclei, creating showers of secondary particles that spread out and cause more damage. Water or hydrogen-rich materials absorb energy without producing as many secondaries. But you'd need meters of water to significantly reduce cosmic ray dose. That's thousands of kilograms of extra mass. Difficult to launch. Difficult to manage in zero gravity. So spacecraft designers face a trade-off. Better shielding means more mass, more cost, more complexity. Less shielding means higher radiation exposure. Current designs accept some radiation exposure as unavoidable and try to minimize it within practical constraints. This is why deep space missions are planned with radiation in mind. Timing missions to coincide with solar minimum, when solar activity and particle radiation is lower. Designing spacecraft with storm shelters, areas with extra shielding where crew can go during solar particle events. Limiting mission duration to keep total dose within acceptable limits. But there's no way to eliminate the risk entirely. Space is radioactive. It's constantly bathed in high-energy particles from cosmic sources. Any human in that environment will be exposed. Any extended stay in deep space will accumulate significant dose. This isn't a problem you can engineer around completely with current technology. You can mitigate it. You can reduce it. But you can't eliminate it. And for an unprotected person in space, the radiation exposure would be massive. Not enough to cause immediate radiation sickness in the seconds before other effects become fatal. Radiation sickness requires high acute doses, usually absorbed over hours or days, but enough that if they somehow survive the pressure and oxygen problems, the radiation alone would guarantee severe health effects or death within days to weeks. In space, there's no protection. The radiation hits you directly. Solar radiation includes ultraviolet light, which causes sunburn and skin cancer with prolonged exposure. In space, without atmospheric filtering, UV exposure would be intense. But UV is actually the least of your concerns. The real danger comes from ionizing radiation. High-energy particles moving at significant fractions of the speed of light. Galactic cosmic rays are atomic nuclei, mostly protons and helium nuclei, but also heavier elements, accelerated to enormous energies by supernova explosions and other violent cosmic events. These particles have energies millions of times higher than anything we can produce in particle accelerators on Earth. When they hit biological tissue, they tear through cells, breaking molecular bonds, damaging DNA, creating cascades of secondary particles. The damage is immediate and cumulative. A single high-energy cosmic ray passing through your body might hit a few cells along its path. Each hit has a chance of causing mutations, potentially leading to cancer. Over time, repeated exposure to cosmic rays accumulates damage. Astronauts on the International Space Station receive radiation doses about 150 to 200 times higher than people on the ground. They're partially protected by Earth's magnetic field, since the station orbits within that field. But even so, they receive much higher doses than we do. Long-duration missions on the ISS, 6 months or more, result in measurable increases in cancer risk. Beyond Earth's magnetic field, in deep space, the radiation exposure is even higher. Astronauts on a mission to Mars would receive radiation doses during the journey that significantly increase their lifetime cancer risk. There's no way to completely shield against cosmic rays with current technology. The particles are too energetic. Thick shielding can help, but it's heavy and impractical for spacecraft. Some shielding materials can actually make things worse by creating secondary radiation when cosmic rays hit the shield material. And this is for astronauts inside spacecraft with some level of shielding. A person directly exposed to space with no protection would receive massive radiation doses. Not enough to cause immediate radiation poisoning in the few seconds before death from other causes, but enough to guarantee severe damage if they somehow survived the pressure and oxygen problems. The radiation would continue to damage tissue, destroying cells, causing burns, leading to organ failure. There's also solar particle events to consider. Occasionally, the sun releases bursts of charged particles during solar flares and coronal mass ejections. These events can deliver radiation doses high enough to cause acute radiation sickness within hours or days. A solar particle event hitting an unprotected person in space would be catastrophic. Even inside a spacecraft with thin aluminum walls, a major solar particle event can be dangerous. This is why solar activity is carefully monitored during space missions. During the Apollo missions to the Moon, astronauts were at risk from solar particle events because they were beyond Earth's magnetic field. They were fortunate that no major events occurred during their missions. A large solar flare during an Apollo mission could have exposed the crew to lethal radiation doses. Planning for future missions to Mars or deeper space has to account for this risk. Spacecraft need radiation shelters, areas with extra shielding